All right, let's dive right in. We're about to explore one of the most, well, mind-bending shifts in technology you can imagine. We're talking about the leap from the computers we all use every single day to the incredibly strange and powerful world of quantum computing. It's all about going from the simple, predictable bit to the mysterious and powerful qubit. So, let's get into it. So here's what we're going to cover. First, we'll look at why our current computers are hitting a wall. Then, we'll meet the star of the show, the qubit. After that, we'll get into the really weird world of the quantum world, see why all this power actually matters, and then, finish up with a reality check on what's next. Okay, think about this for a second. Everything you're doing right now, watching this on your screen, the device in your hands, the internet that's bringing it to you, all of it, the entire digital world, is built on a super simple idea. Things are either a 0 or they're a 1. It's off or on. That's it. But what if you could just break that rule? What if a computer wasn't stuck with just 0 or 1? And that's the question that leads us right here. So on one side, you've got the classical bit. It's the foundation of, well, everything digital. It's 0 or a 1. Simple. But then you look at the quantum bit, or qubit. It can be a 0 and a 1 at the same time. I know it sounds impossible, but that one kind of bizarre difference, it literally changes everything. Okay, so before we get too deep into the weird stuff, let's ground ourselves in what we already know. Let's talk about the comfortable, classical world of the bit. The bit is really the atom of our digital universe. It's the smallest piece of information you can have. It's just a switch. That's it. 0 is off, 1 is on. Every single photo on your phone, every app you use, every website, it's all just a ridiculously long string of these simple on and off signals being crunched by these little things called logic gates to get stuff done. So for decades, the game has been simple. Make the transistors, the little switches that hold these bits, smaller and smaller. And it worked. But now we're hitting a physical wall, a hard one. These transistors are getting so small, they're nearing the size of individual atoms. And at that scale, the normal rules of physics just kind of stop working. We've got massive heat problems and this really bizarre quantum effect called tunneling, where electrons just teleport through barriers they're not supposed to. We just can't keep shrinking things. We need a totally new way of thinking. And that new way of thinking, well, it's a fundamental shift in logic itself. So it's time to meet our hero, the quantum qubit. So this brings us to a qubit's first superpower. It's called superposition. The best way to think about it is like a spinning coin. While it's spinning in the air, before it lands, is it heads or tails? Well, it's kind of both, right? A qubit is just like that spinning coin. It exists in this fuzzy state of being both a 0 and a 1, all at once, right up until the exact moment you look at it or measure it. That's when the coin finally lands. But here's the cool part. It's not just a random 50-50 guess like a fair coin. It's all about probabilities. Before we look at the qubit, we can set it up so that maybe it has a 70% chance of landing on 0 and only a 30% chance of landing on 1. It's like having a weighted coin. And this ability to play with those probabilities, well, that's the secret sauce behind quantum algorithms. Right, so what's the big deal? The crucial takeaway is this. Because one qubit can be in this mix of 0 and 1, a whole system of them can explore a huge number of possibilities all at the same time. And I don't just mean doing two things at once. This is a whole new level of doing things in parallel, a kind of computing our regular machines can only dream of. Let me show you how fast this gets crazy. Your laptop, with 10 bits, can hold one number out of 1,024 possible numbers at any given time. Okay? But just 10 qubits? Thanks to superposition, they can hold and process all 1,024 of those possibilities at the exact same time. Okay, but what if we scale that up a bit? Let's go to 50 qubits. Now, all of a sudden, we're juggling over a quadrillion states at once. That's a 1 with 15 zeros after it. You see, the power doesn't just add up, it multiplies. It's exponential. And that is where this almost unbelievable power comes from. And now for the punchline. You ready for this? With just 300 perfectly stable qubits, you could represent more individual states than there are atoms in the entire observable universe. Just let that sink in for a second. It's a computing space so gigantic, our brains can't really even grasp it. But wait, there's more. Superposition isn't even the weirdest part. It has a partner in crime, a second superpower that is even stranger. It's time to get into the really spooky rules of the quantum world. We're talking about entanglement. Albert Einstein himself called it spooky action at a distance. Basically, you can link two qubits together so their fates are intertwined. They become one system. And here's the spooky part. If you measure one of them, you instantly know the state of the other one, even if that other one is light years away on the other side of the universe. No delay. This instantaneous connection allows us to do things with information that are just flat out impossible in our normal classical world. So let's just walk through how that works. Step 1. You entangle two qubits. Step 2, you could, in theory, separate them by millions of miles. Now, the moment you measure the first one and find out it's a 0, its partner, way over there, instantly becomes a 0 too. No phone call, no signal, just instant. And that perfect connection is a super powerful way to coordinate complex calculations inside a quantum computer. So to play with this weird physics, you need a whole new toolbox. You know how classical computers have logic gates that do simple things like a NOT gate that just flips a 0 to a 1? Well, quantum computers have quantum gates. Some are similar, like one that flips a qubit. But then you get totally new ones. You have a special gate, the Hadamard, whose whole job is to create superposition, to spin the coin. And then you have other gates, like the CNOT, that are specifically designed to create that spooky entanglement link. These are the actual tools you use to build a quantum program. Okay, so we've got superposition and we've got entanglement. They're both pretty weird, counterintuitive ideas. So the big question is, why does any of this matter? What can you actually do with all this strangeness? Well, the potential applications are nothing short of world-changing. On the one hand, a powerful quantum computer could, theoretically, break most of the encryption that keeps all of our online data safe today. That's a big deal. But on the other hand, they could do amazing things, like perfectly simulating complex molecules. This could let us discover new medicines and materials in a fraction of the time. We're also talking about revolutionizing AI and solving massive optimization problems, like for financial markets or global shipping. And this right here is probably the single most important thing to remember. A quantum computer is not just a faster version of your laptop. It's not going to make your video games load quicker. It's a completely new kind of tool. It's designed to solve a very specific set of problems that are so complex that our best supercomputers today would take billions of years to even try. Now that all sounds amazing, right? And it is. But we have to balance all that excitement with a serious dose of reality. There are some huge, huge challenges standing between us and that future. For starters, these quantum states are unbelievably fragile. I mean, the slightest little vibration or temperature change can cause a qubit to lose its quantum magic and just collapse. They call it decoherence. On top of that, the quantum gates we have now are really noisy. They make a lot of errors. And finally, just trying to build a machine with hundreds of these things, keeping them perfectly isolated and cooled to temperatures colder than outer space, well, it's one of the biggest engineering challenges of our time. So let's wrap this part up. The promise of quantum computing is absolutely revolutionary. There's no question about it. But we also have to be realistic. The era where we have big, practical quantum computers that don't make a ton of errors, that's not here yet. It's still on the horizon. But every single day, brilliant people all over the world are chipping away at those challenges. The science behind it is solid, and the potential is just undeniable. So it really leaves us with this one massive question to think about. Once we finally figure it out, will quantum computers kickstart a whole new era of possibility for humanity?